Right, then we'll start again. This is the third unit now. Will you try and work in units, please? You need an A4 pad in front of you now, and I hope you're taking some notes as you go along. There will be support notes on this, but you need to get it into your head first, so the notes are a summary of what you know, all right? Now, the general gas equation here again, Boyle's law, Charles's law, put them together, and that's the general gas equation. Let me give you a tip now. How will you remember these formula? Right, now let me just show you what you do. If you're talking about Boyle's law says that gases at constant temperature. So the T's are equal, so there's Boyle's equation. That's an easy way of remembering it, okay? If it's Charles's law you want, Charles refers to gases at constant pressure. The pressures are the same, so there's Charles's formula. So really, at the end of the day, that's the only formula you want. If it's Boyle, the T's go, and if it's Charles, the P's go. Now there's a useful tip for you, and you don't need to be memorizing them other than that, but that's effectively what you want. That's gas law number 2 done then, Charles, that is, Boyle's and Charles 1 and 2, and I'm going to go on to gas law number 3 now, which is Avogadro's law. Now, as it happens, you're not likely to need much of this law until you get to chemical equilibrium, which is a long way on in the course. So just first of all, it's a statement you need to have. Once you have it, you can then deal with it. It says, in this particular instance now, it says that equal volumes of all gases measured at the same temperature and pressure contain the same number of particles. And that's exactly what you want there, no more, no less than that, okay? So equal volumes under the same conditions of temperature and pressure contain the same number of particles, P, V, T, and N. And according to this law then, you have equal volumes under the same conditions of temperature and pressure contain the same number of particles. They have the same temperature and pressure, so if the volume gets bigger, the number of particles gets bigger. Is that okay? That we're always working with the same variables, and you can only have 2 variables at any one time. If you vary one of these, then the other will be affected by it, provided the rest are constant. But they need to remain constant, that's very important. So, okay, under the same conditions of temperature and pressure, keep them the same, then if the volume increases, the number of particles will increase. That's actually number of moles, we won't go there, but that's fine. Are you okay with that? That's exactly what the law says. And what would that mean then? Well, it effectively would mean that if you had 3 different containers, okay, of 3 different gases in containers, and the containers are identical, they'd be the same number of particles in each container. Equal volumes contain the same number of particles. Now, it wouldn't matter what type of gas you had, right? That might be carbon dioxide. That might be hydrogen. That might be oxygen. That's irrelevant. That would only refer to the size of the particle, which is of no consequence to us, because the number of collisions depends on the number of particles. And that's exactly what you'll be dealing with, okay? So you have 3 gases, and basically they're sealed in chambers like that, and that's what you're working with. As it happens, they would have the same number of particles. Let me get back again then and say this to you here, and back to my syringe. If I was to basically prepare these 3 gases carbon dioxide, I would basically suction up exactly 80 centimeters cubed and seal it. And I would have an exact number of particles in there for that particular gas. And then if I repeated the exercise for the other 2 gases, exactly the same volume, then I'd have exactly the same number of particles in there. So it seems to be the case that the actual type of gas doesn't matter at all. It's the volume of it that matters. The volume of the gas has a certain number of particles in it, and if all the gases are at the same temperature, these 3 containers are in the same room. So they're at the same temperature, the same pressure, so they'd have the same number of particles, and that's effectively all they want from you. Equal volumes contain equal number of particles. Now, where that will raise its head for you, I've said already, is under chemical equilibrium. When they start talking about the fact that 2 named gases are allowed to reach equilibrium at a stated temperature, the minute you hear 2 gases, okay, same temperature and pressure, Avogadro will hit you immediately. When they start talking about 2 different gases under the same conditions of temperature and pressure, It's Avogadro's law. So that's a way of saying, oh, you have the same volumes, so you have the same number of particles, so you have the same number of moles. And therefore, you'll apply that to your equilibrium system. Now, I haven't it done, and you certainly haven't it done in 5th year. I'm aware of that. But I'm just saying to you that that will raise its head again later. Now, I don't really want to go places with this, but I'm just going to give you 1 or 2 things with this. Look at 2 possible deductions here. You do not need to take these down. They're only illustrations. If you took hydrogen gas and chlorine gas, you'd get hydrogen chloride. That's a balanced equation. Hydrogen gas and chlorine gas, you'd get hydrogen chloride. And we'd balance that equation with a 2 there. So, if you had 1 volume of this and 1 volume of this, you get 2 volumes of this because the number of particles are doubled here. Okay, that's basically the same thing. Particles and volumes are interchangeable, and that's exactly it. Okay, that 1 volume and 1 volume will give you 2 volumes. Now, based on the premise, that's a gas, that's a gas, and that's a gas. Now, I wouldn't worry about that. That's not the important thing. The important thing is you can state the law and you can describe what is meant by this law. The law simply means nothing more than if you have a certain volume of a gas at a stated temperature and pressure, and you have a different gas at the same temperature and pressure, they would all have the same number of particles. Okay, very, very important. And once you've got to that, volumes and molecules are interchangeable. 2 hydrogen gas, 1 oxygen gas gives you 2 steam. You need to be careful there with that, because when we write H2O, we think of different things, don't we? H2 plus O2 goes to H2O. There's 2 there. That's a gas, we probably know that. That's a gas, but you'd have to write a G here, or of course we'll be thinking it's the liquid. That's steam, of course. Okay, so you can either say 2 molecules, 2 particles, plus 1 particle gives you 2 particles, or 2 volumes, 1 volume gives you 2 volumes. Okay, and that's effectively that. Now, that's not something you need to work on immediately. That's not important at all. But it is important you can state this law, and I hope you can do that. Equal volumes of all gases, measured under the same conditions of temperature and pressure, contain the same number of particles. Good. And we've only 1 gas law left, and that's known as Gay-Lussac's law. Now, this particular law is a dangerous law because it's often confused with other ideas, and we need to be careful with it. Okay, so just bear with me while I elaborate a little bit on it. First of all, everybody needs to know that this law refers to reactions involving gases only. It cannot be used for any reaction where not all involved are not gases. For example, if you had something like hydrogen plus oxygen going to H2O. All right, now you could balance that several ways. You could put a half in there and that would be balanced. If that was a gas and that was a gas and this was not a gas, then you cannot apply that law. It must be all gases. This would have to be steam, and that's why I write the G in there, so be careful. And there's many of them you could have there now, and you could be very confused about that. Be careful, please. You must have all gases here, and you must have all gases on this side, or you can't use that law. Okay? It's called the law of combining volumes. In reactions between gases, and I like people to put in there, in reactions between gases only gases. Okay, the volumes of the reacting gases and the volumes of the gas products are always in the ratio of simple whole numbers, provided the volumes are measured at the same temperature and the same pressure. And I'm illustrating that then with various examples. Hydrogen gas will react with oxygen and produce, be careful now, will produce steam. You'd have to write a G in there, or you'll be thinking that's water. Okay, steam, gas, gas, and gas. Okay, very important. In physical chemistry, they always write the state of the reactant or product in brackets after it. They'd always put in the letters G, aqueous for solutions, L for liquids, and S for solids. They'd always put them in, but I'm just asking you to be aware that in this case, that's meant to be steam. And of course, it means that they're simple whole number ratios, 2 to 1 to 2. Of course, there's a bigger problem here for you, and you need to realize this. Here I go again. You need to go back in chemistry to go forward. If you have difficulty in writing chemical equations, that's a different problem, but you need to deal with it now, please. Okay? If you have difficulty, you need to get the chemical formula right first, H2O2 and H2O. Balancing them is another exercise. And it's very important you go back and sort that out before you move forward here, because you're suggesting that this is difficult when in fact it's something in your background that you haven't developed yet. So feel free to go back and ask me questions on them if you have to. Here's the next one. If you reacted hydrogen gas with chlorine gas, you get hydrogen chloride gas. And here we go again. I suspect most chemistry students who see HCl written are going to say hydrochloric acid. I think they are. I think that's what they'd say. You have to qualify that. It would be very important to put a G after it. That's hydrogen chloride gas. As it happens, hydrogen chloride gas is very soluble in water. And when it dissolves in water, you get hydrochloric acid. Brilliant. That's what it's about, and you have to be aware of it. HCl, okay, G. You have to have a G in there. I'm just pointing that out to you. Now, be clear, please. Only gases or it won't work. So the ratio is 1 to 1 to 2, and you have to balance that equation. Right? And we move on from that then. The next one. There you go. If you reacted nitrogen gas with oxygen gas, you get nitrogen dioxide gas. Okay? And the ratio is 1 to 2 to 2. Simple whole number ratios. The volumes of the gaseous products are always in the ratio of simple whole numbers, provided the volumes are at the same temperature and pressure. If they were in the same reaction flask, of course, they'd have the same temperature and pressure. That would be normal, wouldn't it? It would. And next, nitrogen monoxide, over there, reacts with oxygen and gives you nitrogen dioxide. Now, I'm not taking this for granted at all. I'm not saying you can write out all those equations, but you need to be in a position to know if they gave you a certain amount. Could you balance this equation? NO plus O2 goes to NO2. NO plus O2 goes to NO2, okay? Now, you start from the left. One nitrogen, balanced. One oxygen, three oxygens, and there is two oxygens here. So we've one too many here. Now, there's many ways of balancing an equation. You could put a 2 in there, but then you'll have to adjust the nitrogens again, so that won't work. Always take the element on its own. I can put in a half there. Half of 2 is 1. That's 2 oxygens and 2 oxygens. It's balanced. Now, you know, don't you? I'm not talking about half a molecule. I'd be talking about half a mole of it. So that'd be very important that you'd be aware of that. But that's it anyway. And I can multiply by 2 to get rid of the half if I like. Okay? So if I put a 2 in there, you don't write number 1 ever, as you know. There was no 1 written there, but just one of them. And that'll be 1, and this will be 2. If I multiply by 2, I got rid of the half. That's fine. So the ratio is 2 to 1 to 2. And how would you show that then? I'm going to show you now some ideas to how you might show that. You would take 2 gas syringes. Now, this is not an easy task to carry out. There would be issues with it. You take 2 of them. I have the one here that I showed you already. And you take a second one and you join them with a piece of rubber tubing there. Some people would put a tap in the middle so you could control them. You prepare one gas in the lab, like oxygen. Okay, would you know how to prepare oxygen in the lab? You prepare oxygen in the lab by reacting hydrogen peroxide with manganese 4 oxide. And you would get, no, sorry, I'm only mentioning that in passing, but I'm saying to you that you would. And then you'd suction up the gas like that into this, and you'd close the tap. And then you do the same with the second one. You take the nitrogen monoxide, a dangerous gas, but the monoxides are dangerous, and you'd suction that up as well, and you close the tap. And you'd have the 2 of them then set up like that, there and there. Are you okay with that? And then you'd open the tap and you'd mix them. And how would you mix them? You'd push the pistons in. You'd push this piston in and the other one would go out. You'd mix the gases, in other words. And then you'd push that piston in and this one would go out. And then you'd push that in and that would go out. And you'd do that a couple of 100 times. So you'd push it out and then to go back in, and then you'd push it here and this would go back out, and you'd push it here and that. You're mixing the gases. And having done that a couple of 100 times, you'd find 2 things would happen. Number 1 is, these are 2 colourless gases. It would turn brown. Colourless, that's brown. The gas will start turning brown, proving that you're causing that reaction to take place. These 2 are reacting and they're going to turn brown. But the more important thing is, you started with 100 centimeters cubed of that, 100 on the scale, 100 on your scale here, okay? And you had 50 of that, 50 on the scale here. When you'd be finished, that's 100 and 150, that's 150, 150 is 150. But when you'd be finished, that volume would have reduced to 100. And that's Gay-Lussac's law. Okay, the ratio 2 to 1 to 2. Okay, so 100 plus 50, because they change into a different gas, you get a different volume. Now, that's difficult enough, I'd have to say to you, but the assurance I want to give you is it would be examined in isolation. It's not likely to be linked to anything else. It would be exactly state Gay-Lussac's law. It would be exactly that. State Gay-Lussac's law. And then the next thing they would say to you would be, how would you show this in the lab? And all they'd want is a simple illustration that the ratios to one to the other is, in this case, because of that equation to be 1. You could have taken any one of them, by the way. Hydrogen and oxygen in here, and you'd find that the volume would go down. Now, some of these could not be carried out at room temperature, but just a sense of that particular law. Now, the first two laws are very important. Avogadro's law will be very important in a later part of your course. And Gay-Lussac's law stands alone. I'd be happy to say that to you for the moment. You might have questions for me on it at some stage. I understand that. But that's what you want for the moment. I hope that's okay. Now, I'm going to leave that and show you where I'm moving from here, because I need you to have a sense of place with this as regards what we're doing. Now, the one thing I haven't done with you yet, I'm going to do it now, is I haven't touched on STP. Going back again now, Brownian motion, that's simply an acknowledgement that particles of gas are constantly moving. These are the main properties, and the gas laws are based on them. The 4 gas laws have to do with the fact that if you keep any 2 of these constant, you can study the effect of the 3rd on the 4th. That's effectively it, okay? And just please make sure you can state your 4 laws. And can I appeal to you again now, please? Stop memorizing them. There is no need for that. There's a concept there. Think about it, and you'll be great. You'll do very well, okay? That's important. They're the gas laws. STP I passed over. That's the general gas equation, P1 V1 over T1, P2 V2 over T2. We're going to substitute that for a better formula shortly. This one has issues with it that I'll talk to you about later. I'm going to talk to you about STP means standard temperature and pressure. And they are recognizable now, and I have to tell you this, you can look them up. You don't need to know them, but I think I'd expect any self-respecting chemistry student to have a ballpark figure of these. Standard temperature is 0 degrees Celsius, but they generally want it in metric, so it's 273 Kelvin. Okay, 273 Kelvin is preferred. Right? Now, I'm saying that to you from the point of view, if you go to look it up, I'm looking for a page for you, you'll find it on page 64 of your formula tables. Page 64 of your formula tables, you can look that up. Okay? And the standard pressure is 1.013 by 10 to the power of 5 pascals. Are you impressed? That's that, okay? You can look it up, okay? But that's it. They often abbreviate it to 101 kilopascals, okay? They're the 2 you'd want anyway, very important, right? They're the 2 you'd want, okay? By the way, pascals is the metric unit. You couldn't use kilopascals, you'd have to go back to that if you were doing it, all right? But 101 kilopascals and 273 Kelvin are standard temperature and pressure. Why am I telling you that? Because the following question might come up. I'm back to my syringe again. Now, it's great to have something concrete to work with. That's always important, that you're relating to something, that you're not just learning words, okay? Let me put this in here again. I'm going to get 80 this time if I can. I'm locking it at 80. I think I have it there. There's 80 centimeters cubed of gas in that then, all right? 80 centimeters cubed of gas. You have it, right? Now, I'm asking you a question now. There's 80 centimeters cubed of gas in there. The temperature of this room is 20 degrees. And the pressure is 100 kilopascals. I'm asking you the question now, what would the volume of this gas be at STP? In other words, do you know what you're doing? You are, of course, going to use your general gas equation. You're going to use your general gas equation for that as follows. Okay, here we go. P1 V1 over T1 equals P2 V2 over T2, okay? We were given the volume there, I said 80, right? At a pressure of 100 kilopascals and the temperature I said was 20 degrees, I'm leaving it at Celsius, equals. And you want to know the volume at STP, so the answer is, do you know those two? Can you get standard? They're on the board here, right? But that's the point, you know where to go and get them. I gave you the volume in the lab at a stated temperature and a stated pressure. And I asked you, what volume would it have if it was STP? Now, that's something you might need to use on occasions. So the standard pressure is going in there. That's 101 kilopascals, right? And the other one is 273. And I've made a serious mistake, of course. Deliberately, I hope. But I've made a serious mistake. That's fine. I'm looking for the volume at standard temperature and pressure. The units must be the same on both sides. That's 20 degrees Celsius. That's Kelvin. You can't do that. Okay, it's very important that you recognize this. The units must be right. Okay, so if you are going for that, you have to write that obviously. 273 would be 0 degrees Celsius. Either change that to degrees Celsius or change that to Kelvin. If you change that to Kelvin, you're adding 273 to it and it will become 293. Okay, and now you'd be able to do that. Be careful. The one danger with that formula is, I'm not mad about it now, and I would lead you in another direction in one of the future modules. I'm not mad about this because, frankly, what it does is you're likely to mess up the calculation. There's easier ways of doing it, but you may be obliged to use this one, so you must be ready for it. You can use any units you like here, provided they're the same on both sides. Pascals, pascals, kilopascals, kilopascals. Liters and liters, centimeters cubed, centimeters cubed. That's okay. Okay, and down here, degrees Celsius, degrees Celsius, degrees Kelvin, degrees Kelvin. They must be the same units. You'd want to put an asterisk on that formula, a heads up that you wouldn't make that mistake. That'd be a dreadful mistake to make now in light of the fact that you knew how to do it and yet you messed up. So please be careful with that. It's very, very important. All right. Now, I think I have that sorted for you. And I think we can leave that for the moment, that you have the bulk of that done and we've nothing to add to it. I'm going to move on, if I can then, please, to the kinetic theory of gases. Okay, the kinetic theory of gases. Now, this stands alone. I would like to tell you that you must be very clear on this. Ultimately, when I get to here, ideal gases, I'm going to replace the general gas equation with a more efficient law, okay? A more efficient one, but that's for another module and we'll get to it in due course, and I just want you to be ready for that. Very good. So here we go then. The kinetic theory of gases is as follows, right? And I'm going to work my way through this. Now, will you be attentive to it, please? It's vitally important that you wouldn't be making any mistakes here, okay? And that you would know precisely what's happening. The kinetic theory of gases. This theory explains many of the properties of gases and the gas laws. Now, it's a theory, and can I just give you a moment, please, to understand what theories are and what their function is. A theory is correct until it's proven wrong, right? If the lights go out in this room, we immediately logically explain it with a theory. Oh, there's a power failure. And then we look out the window and we discover there's not a power failure, so that theory is wrong. We have to make up a new one. Maybe they didn't pay the electricity bill. Another theory. Do you know what I mean? A theory is our way of logically explaining something we observe. It doesn't have to be sophisticated, but you do need to understand that theories are based on some kind of observation. And let me say to you, a theory is correct until somebody proves it wrong. And that's the way you need to be thinking of this. So this is a simplification of gases for you, the kinetic theory of gases, right? And there shouldn't be any issue with it at all. You should be able to manage it. This theory explains many of the properties of gases and the gas laws. And I'm very quickly repeating Brownian motion here again for you now, because that could become an issue in due course, and I'd ask you to be aware of that, right? So Brownian motion is stating something very simple there. This leads to the conclusion that gas particles are in constant random motion. That phrase there you throw out all the time. The particles are always running around the place, and that's very, very important that you have that and that you'll be able to deal with that more than anything else, okay?